Pythagorean theorem only works for right triangles. So if you have a right triangle, part of what you need to be able to do is identify the specific parts. But the longest side, which is directly across from your right angle, which would be the biggest angle, is the hypotenuse. Okay. Has to be across from the right angle.
Would it be called something else if it wasn't in a right angle? Would it be called something else if it wasn't in a right angle?
It would just be a side. So specifically in a right triangle, we do have a hypotenuse, and then the part that is the two sides that are not a hypotenuse would just be considered legs, and it is the legs that make up the right angle. Now, the theorem itself says if you're going to see it a squared plus b squared equals c squared, but everything else we're going to use it for is going to be more usable if you put c squared first. So c squared is the sum of the square of the other two sides. Okay. We are going to be able to use this to check if triangle is a right triangle, but we're also going to be able to use it in a comparison to see if it's not a right triangle. We should be able to tell if it's acute or obtuse based on how some of this comes out. Okay. One big piece of information, though, is you use 2 out of 3 to solve for a missing side. Okay, so you need to know 2 out of 3 of the sides. If you only know one of them, it's not that you're not going to be able to find what you're looking for, it's just there's going to be a different method probably that you'll have to use. Theorem only works with 2 out of 3 known values. Okay. So we will apply this in a moment, but another thing to look for, which shortens your work, are Pythagorean triples. A Pythagorean triple is a set of 3 non-zero numbers that satisfy the theorem when we plug them in. And the only thing you have to be careful of with plugging them in is C is the hypotenuse. I should have put that up here. A, B, C. You might want to add those in. A and B are considered the legs. C will always be the hypotenuse. Critical piece of information. So the longest out of your 3 numbers should be by itself in your equation. Okay, so we have a couple triples that are worth your time. One especially, they give 4 sets in the book. 2 of them I'm not even going to have you write down because you're probably not going to remember them anyways. But this one is the best one to remember. 3, 4, 5.
Wait.
5, of course, would be the hypotenuse, and 3 and 4 would be the legs. And the reason it's worth your time is if I have a triangle where I see the legs are 3 and 4, I don't have to use the theorem. 5 should be the hypotenuse because 3 squared is 9, 4 squared is 16, their sum is 25, and 25 is the square of 5. Okay, so you are guaranteed. Now, if I said, well, if the leg is 3 and the hypotenuse is 5, then the other leg should be 4. Okay, so in that particular, now if I said the leg was 3 and the hypotenuse is 4, then it doesn't work. But the nice thing about knowing that triple, and you will run into it, is say you're working on a problem and one leg is 6 and the other leg is 8. Even multiples of the triple work. 6 is twice as big as 3, right? And 8 is twice as big as 4. So your hypotenuse should be twice as big as 5. So that should be 10, and I didn't have to use the theorem at all. Now, if you use the theorem, you'd still come up with that as a hypotenuse. But if you know that triple, it will save you some time on occasion. Sometimes I notice it, sometimes I do the work anyways, and then after the fact go, oh yeah, that was a triple. So we've got that one. Another one, which is handy, but you won't notice as readily probably, is 5, 12, and 13. And of course, 13 would have to be the hypotenuse. In all honesty, the only one I've ever committed to memory is the 3, 4, 5. Consecutive numbers, 3, 4, 5 are easy to remember. So, all right, so let's apply the theorem. We're going to be finding side lengths. When you're given both legs, it really doesn't matter which one you choose to call A or B, because they're going to be squared and added together anyways. So that part doesn't make a difference. C, though, again, has to be the hypotenuse. So in this case, we are missing C. So applying the theorem, C squared equals A squared plus B squared, we would have C squared equals 20 squared plus 21 squared. So that would be 400 plus 441. And occasionally I see some bad algebra. If you're already looking going, oh, that's C squared and I want C, so I'm going to have to take square roots. You are on the right track, but sometimes I see people take the square roots here and then they'll just do it individually, which is against the math law anyways, but there'd be no point in undoing what we just did. So you do have to do the sum first. So it's C squared equals 841. And the form of your answers is really going to depend. If it's a real life context, you're probably going to use the decimal. Okay? If I was finding the length of a walkway in a park, it wouldn't make a whole lot of sense to go, well, that's 10 radical 3 meters. That we just don't do that. So normally, real life context, you're going to be able to have a decimal, but you want to pay attention to the directions because it'll either say round to the nearest tenth or leave your answer in simplest radical form. In this case, when we take the square root, you're going to find that 841 is a perfect square, so C would be 29. So remember, the one above, you had 2 legs. This one, you have 1 leg, 1 hypotenuse. So this is going to look slightly different. which one is C?
X? No, 20.
20. It's the hypotenuse. So C, that's really the one you need to identify, because that one's going to go by itself. So this would be 20 squared equals x squared plus 8 squared. When you have both legs, you're going to be adding, but when you have one leg and one hypotenuse, it will involve subtracting. So we have 400, and for 8 squared, that's 64. So we're going to have to subtract 64, and you get 336. And of course we want x, not x squared. So we're going to take the square root. Cell phones need to be put away, please. Okay. When you take the square root of 336, you're going to notice it is not a perfect square. And there's a section in your homework where the 1 through 6, those will come out to nice whole numbers. Then you'll have some where you have the hypotenuse and the leg, and those will come out to nice whole numbers. And then you're going to have a section where it's a mixture, and they do not come out to whole numbers. That is the one where you're going to have to simplify radicals. Okay, so there's a section of those. I'm going to save you the time on the tree, but remember, if it doesn't say round to the nearest tenth, you need to simplify your radical. Okay, so if you did the tree, you would have 4 2s, a 3, and a 7. So looking for our pairs, we have 2 pairs of 2s. So what would this simplify to? Yep, 4 radical 21 would be x.